In this session, we're going to talk about image reconstruction. Now, the reconstruction process has been split into two parts. In this first part, we're going to discuss the general workflow, the source geometry considerations, storing the data as it's acquired, pre-processing, and then lead into part two, where we actually detail the mathematical formalisms and generate a general understanding of how the reconstruction process works. So the workflow in its broadest sense starts with intensities, so photons interacting in detector channels. Those intensities that are recorded as a function of rotation angle and as a function of detector channel location at each rotation angle then have to be converted into attenuation data, as was discussed with the Beer-Lambert law. The attenuation data is then reconstructed into an image in some form, and there are several different ways that we can do that process. We then have a series of post-processing and visualization steps. So we could arrive at, say, a MIP, which is a maximum intensity projection, or a surface shaded display representation, or a volume rendered representation, and in fact there are several others which we'll discuss later. So first of all, we have to consider the geometry of the source and detector configuration, because that's going to relate to how the data is actually stored. So we're going to see that we actually need, in a third generation scanner where we have a large open fan beam, two angles to index, to uniquely index, that is, each ray path. And we can do that with the Greek symbols theta and sigma. So theta represents the rotation angle, also called the projection angle of the scanner, and sigma represents the angle from the central ray, the 0 degree line, to a given ray path. And that angle can be positive or negative if it's to the right or to the left of the central line at a given angle theta. Okay, one thing that you should consider is that most of the reconstruction processes relate to, as this is a fairly elementary introduction to the course, relate to back projecting parallel rays. So although the data is actually acquired in a fan beam, we'll generally be discussing the back projection of the rays in a parallel configuration, as it's more straightforward mathematically to discuss. So to give you an idea of some of the numbers, the source to detector distance is generally of the order of a meter. The detector element spacing is generally of the order of about a millimeter or so, or even sub-millimeter, and we expect sub-millimeter spatial resolutions. Okay, so as I said, depending on whether we've got a first generation scanner or a third generation scanner, the way in which each ray path is indexed will differ. So for a first generation scanner, and in this course, as I said previously, a lot of the discussions will relate to first generation scanners because the parallel acquisition of the data is more straightforward if we're solving problems along the way in order to solidify your understanding. So we can see that for a first generation scanner where we have parallel ray paths, so we've assumed a translate rotate configuration. Each ray path is parallel to the others at a given projection angle, and so our indices for each ray path are x subscript r, which is the offset location of the detector and the source, the translate offset, and theta, which is the projection angle. For a third generation scanner where we have the fan beam, we would have theta and sigma, as I've previously detailed. And we have to solve the Beer-Lambert law, so we have to undo this projection data in order to get back to our image. Now I'm going to introduce you to a new term which is called sinogram. So the sinogram is a convenient way in which the data is stored when it's acquired during a CT scan. So in order to give you a representation here, I've just developed a cartoon. So here we can see the translate rotate geometry that we've discussed previously. and we can see that we have a phantom which comprises a circle, a square, a small point, and a bar or a line. Now, if we consider for each of the red detector channel locations at this given projection angle, which is 0 degrees, if we consider the intensities which have then been converted into attenuation values, we would have a number in each one of those red detector channels. And if we plot those numbers as colours, where black is a low number and white is a high number, we would get the distribution on the right hand side of the slide here at 0 degrees. So the x-axis of the sinogram runs from -r to +r, and the y-axis is going to be rotation angle. Now if we rotate round, before we rotate round, just to reiterate the point that the sinogram x-axis would change for a third generation scanner, and it would go from -gamma to gamma, which satisfies the range of sigma values for the different ray path offset angles. So if we rotate round to 90 degrees now, and assume we've filled in all the sinogram steps from 0 to 90 degrees as we've rotated round, we can see that the attenuation data starts to trace out these waves. And this is why this storage mechanism is called a sinogram, because any fixed point, if we take a fixed point in the phantom and we project through it and then rotate, project through it, rotate and project through it, it will move through the sinogram like a sine wave. So if we keep going to 180 degrees and then 360 degrees, we can see now we have the full collection of the sinogram. So the sinogram there on the right hand side represents all of the data that we've acquired. So that's all of our ray paths have a unique location in this 2D plot. So we can see the two brightest white points there represent when the scanner is at 90 degrees and 270 degrees, and they represent the ray path that would be going through the long bar line there, because that would be the highest amount of attenuation for a ray that has to traverse all of that material in the bright white bar at the bottom of the phantom. Now, as part of the course, you'll also be using our optical CT scanner in order to improve your understanding of the CT reconstruction process. So here we can see for a series of cones that have been placed in our optical CT scanner, as the CT scanner rotates and rotates the cones that are in the phantom, we can see the sinogram there being generated. And we'll come back to that in the practical class. Right, so once we've collected our data, so we're still not at the stage yet where we can actually then reconstruct it. All we've done so far is set the CT scanner in motion, it's rotated round to various angles, flashed the X-ray source at each of those angles, collected a set of data in the detector channels, and then we've dumped that data into our sinogram as a handy way of storing the data. And just to note that we would have a complete sinogram at each one of our Z locations for an axial step and shoot configuration. As we're going to see for helical scanning, things get a little bit more complicated. So on the left hand side here, circled in yellow, we can imagine we have a CT scanner that's done one complete rotation at the first patient bed location, moved the patient bed, and then done one complete rotation at the second location, and we have our two sinograms that we've collected. So we can see the x-axis on this plot would be the Z location, the y-axis would be the rotation angle, and the 2D surface represents the data in the sinogram that we've collected at each one of those Z locations. Now if you think about it, for a helical scanner, because the patient bed is continually moving as the gantry rotates, we don't have a complete set of rotational data at each Z location. So for an axial scanner, we're at a single Z location, we have a complete set of rotations, and all of our data therefore lies in a vertical plane. For a helical scanner, we don't have that. For a helical scanner, we would have a tilted plane. And we can see here the separation between tilted planes is governed by the pitch that we set the scanner to. So if we increase the pitch, the tilted plane would have a more gentle slope. If we decrease the pitch, it would have a more vertical slope, a more severe slope. A more upright configuration. And if we take the pitch to being 0, remembering the pitch essentially being a representation of how far the patient bed is moving per rotation, if we ignore the slice thickness for now, then if we wind that right back, eventually we'll get back to having our axial step and shoot configuration with a vertical plane. So we can see here that in order to do the reconstruction, we need to get from our tilted planes in our sinogram space to our vertical planes. And we do that using this process called interpolation. So we can take a data point at one location, a data point at a next location, and then interpolate between those 2 points to get a data point in between. And here we can see a cartoon showing that. So if we can imagine, we've collected 3 sinograms worth of data with our helical scan configuration, and we want to first convert the data to being, so that would be the blue, the red and the green lines, and we want to convert the data so that it's equivalent to the data we would have collected on the black line before we can do the reconstruction. So just to reiterate, the blue, the red and the green lines on this plot represent the helical data that we would have collected, and the black line represents the data we want to synthetically generate from our blue, red and green data in order to make the reconstruction process straightforward and as if we had just used an axial scanner in the first place. Okay, so there's one other consideration with interpolation, and that is, you can imagine that if I'm interpolating between 2 points, if I spread those 2 points far apart, now as the CT scanner is rotating around and acquiring data, if those 2 points are far apart and I want to interpolate to a data point in the middle, if I've got bone here and soft tissue here and I interpolate between those 2 points, I'm going to get a point in the middle that's a weighted average of the bone and the soft tissue. Now if that point in the middle is actually bone or is actually soft tissue, the value that I synthetically generate is going to be far off. So in interpolation, if I know I've got to interpolate the data, what I really want to do is have 2 points very close to and either side of the data point that I want to generate synthetically. So if I've got bone and I want to generate a point in the middle which I know is going to be bone, then if I take a weighted average between the value for bone and the value for bone, I'm going to get back the value for bone. So in general, having data points closer together in the CT reconstruction process means the interpolation is more accurate. Now there's a cost benefit here, and you can imagine that in order for me to get my data points close together, that means I want the pitch to be small, so I'm going to wind really tight coils in my corkscrew helical motion. But the downside of that clearly is dose. It means I'm going to be giving more dose to the patient. So as with everything that we discuss in physics, there's always a trade-off, and so you have to optimize that trade-off in order to get the best interpolation, which is going to give you accurate results, but not giving too much dose to the patient. Here we can see the result of that synthetic generation process called the half-scan reconstruction. And on the left-hand side, we can see that as I rotate round, before we said in our interpolation algorithm, in our tilted sinograms, the 2 tilted lines are 1 pitch apart. which means, so I was at 0 degrees when the scanner started, I rotate all the way around the 360 degrees, and then I'm back to where I started, which means I can interpolate between those 2 points. Now, you can actually play on the fact that at 180 degrees, the view through the patient should look the same for a first generation scanner, that is, ignoring the fan beam considerations. The view should look the same as the view from 0 degrees. So what I can actually do is, rather than having to wait for the scanner to rotate all 360 degrees in order to do my interpolation, what I can actually do is take the data at 0 degrees and the data at 180 degrees and interpolate between those data points. And this is called the half scan reconstruction. So on the right hand side of this plot, the black line, the solid black line, represents all of the data that we would collect when we're scanning if we were just doing 360 degree interpolation. So if we were only interpolating between the data that we collected at 0 degrees and then the data that we collected when we've wound all the way back round to the 360 degree point, which is the same as the 0 degree point. Now the dashed line represents the synthetic data that we can generate in order to improve our interpolation process. Right, so the pre-processing gets a little bit more complicated than that, in that so far we've discussed interpolation between 2 points. Now you can actually do interpolation between more than 2 points. So if you've only got 2 points, then the only type of interpolation you can do is called linear interpolation. So you have to assume that the data lying between the 2 data points that I've actually collected varies linearly. Now if you've got more than 2 data points and you want to find a point in between the set of data points, you can actually fit a function that's non-linear to that data. And when we do multi-slice helical scanning, because we might have several hundred detector rows collecting data in the Z direction all at the same time, we can actually do more sophisticated interpolation. Okay, so that brings us to the end of our initial discussion in the reconstruction stage. So in the next session, we're actually going to go on to discuss the Fourier reconstruction process, back projection, filter back projection, and iterative reconstruction in more detail. So to summarize what we've taken away from this session, you should be aware that the ray paths that are collected in a CT data set can be indexed by sigma, theta, and Z. So that's for a third generation helical scanner. Now in a first generation scanner, we would swap out the sigma for the X with the subscript R, meaning the offset position for the translation of the source and detector channel. Helical data can be reconstructed onto any plane, unlike axial data, which is why we have a big advantage there. So remember, we said for axial data, we're at one Z location, we collect all 360 degrees, which means we can only actually reconstruct the data at that location because we don't have any other data either side. For helical scanning, because the gantry is continuously moving while the patient bed is continuously moving, we can actually choose our reconstruction planes to be anywhere for the volume. Interpolation is required as a pre-processing step prior to the reconstruction. Multi-slice helical offers us advantages over single slice helical because we can do nonlinear interpolation, and the half scan reconstruction process offers us a way to improve the temporal resolution or the accuracy of our interpolation.